So let's try to do an example with the method of least squares. Now, you guys have probably seen systems of two equations and two unknowns, something like 2x plus 3y equals 5, and 3x minus y equals 7. You guys should know that as long as your two lines are not parallel, which would mean there are no solutions to both equations, and that they're not actually multiples of the same line, which would mean they're on top of each other and there's infinitely many solutions, then you would have exactly one solution for x and y in this sort of a situation. But what happens if we bring in a third equation, something like, I don't know, that, just to make something up? Well, in general, there's not going to be any solution that meets all three. I mean, you have a line here, a line here, and a line here. It's not necessarily going to be true that the point on the point where those two lines meet is the same as this point and this point. I mean, you could have situations where everything works out nicely, but in general, that is not going to be the case. So the idea here behind the method of least squares is that we're not asking for an exact solution. We want the best approximate solution that we can get. Something where, hey, if we have something like this, we can say, well, hey, that's a pretty good point. It's not too far away from satisfying all three equations. So let's make an example. I'm going to have to write small because there's a lot of writing in these things. Let's do x minus 2y plus 1 equals 0. I'm going to write my constants on the left of the equal sign and leave zeros on the right just to match the notation that's in the book. Let's try 2x plus y plus 5 equals 0. And let's finally try 3x minus y minus 1 equals 0. Okay, so in order to solve using the method of least squares, what I'm going to need is I'm going to need the sum of the ai's squared. Now the ai's are the coefficients of x. So here, I'm just going to take each of the coefficients of x squared. I get 1 squared plus 2 squared plus 3 squared. So that's going to be 9 plus 4 plus 1. 14. And then for the bi's squared, I get, well, now I'm looking at the coefficients of y's. So the coefficients of the y's are going to give me 4. That's minus 2 squared, plus 1, that's 1 squared, plus 1. So that gives me 6. Now, the ci's are going to be the constant terms, but actually we don't need the ci squared. What we do need is the ai bi's. So that's going to give me, well, 1 times minus 2, right, because it's the first a and the first b, plus 2 times 1 plus 3 times minus 1, which gives me minus 5 plus 2 minus 3. I'm going to also need the ai ci's, so that's going to be 1 times 1 plus 2 times 5 plus 3 times minus 1. So this is going to be 10 minus 3, so that brings me down to 7, 8. And then I need the bi ci's. So that's going to give me minus 2 times 1 plus 1 times 5, and then plus minus 1 times minus 1. So this gives me 5 plus 1, which is 6, minus 2 is 4. And then, in order to find our best approximation, what we do is we follow the formula that's here on page 466 from section 12.15, which says we take the sum of the ai squared. So I get 14x, and then plus, then I take the aibi's minus 3y, and then the aicis plus 8 equals 0. And then I take the aibi, so I get minus 3x there, and then the bi squares, so that's going to be plus 6y, and then the bicis, so that's plus 4 equals 0. And solving that system of two linear equations is going to give us our approximation. And of course, in this case, this is a pretty easy one to solve, because I can just multiply this equation here by 2, and the y's cancel out. So, but I'll leave that for you guys. It's 2 equations and 2 unknowns, and that should be something you guys know how to handle. But this, in general, is how we would do the method of least squares. Now, we could do it with 4 equations instead of 3 or 5 equations or 6 equations. The method is the same. It's just with 4 equations, we'd get a sum of 4 terms at each step instead of 3, and with 5, we'd get 5 terms, and so on.